In this video, I'm going to walk you through colligative properties of solutions, and then eventually we'll do some problems involving these colligative properties. Colligative properties for solutions here depend on the concentration of the solute particles themselves, not the actual type. All right, so the idea here is when you're going to form a solution and you're adding a solute to a solvent, the IMFs of the solvent get interrupted here with the addition of the solute. So this changes the properties here of the solvent. And that's what these colligative properties relate to. When you're forming a solution by adding a solute, what's actually going on here now with the solution? So basically, we're going to look at a few properties. Anytime you add a solute to a solvent, we're going to change certain physical properties here, including the vapor pressure lowering, the boiling point will go up, the freezing point will go down, and we'll look at how this impacts osmotic pressure. So we're going to walk through all of these properties and see how adding a solute to a solvent affects them. The first colligative property I'm going to look at here is vapor pressure, all right? And the vapor pressure is always lowered here. So anytime you're adding what we call a non-volatile solute, we're always going to lower the vapor pressure of the solvent. So basically, when you form a solution, the vapor pressure of the solvent is always going to go down. Just to reiterate here, volatile means that a particular substance has a vapor pressure. It can leave the liquid phase relatively easily and form a gas, creating a vapor pressure. A non-volatile substance would have no vapor pressure. Basically, the IMFs are too strong, and the substance can't leave the liquid phase as easily to form the gas to create the vapor pressure. The basic way to think about this is that when you add a solute to the solute gets in the way and it prevents these solvent molecules from escaping into the gas phase. So the vapor pressure goes down. All right, you really need to think about that. The solute gets in the way and prevents those solvent particles from leaving and turning into a gas. So the vapor pressure is always going to be lower here. Right? So if you look at this picture here on the left, you can see the solvent by itself. There's a certain vapor pressure created here in this tube by the solvent. But then if you look, when the solute is added to the solvent and you're forming a solution, take note, you can see here, you definitely don't have as many molecules in the gas phase. So the vapor pressure would be lower. You have a lot of molecules here in the gas phase, definitely less when the solute is added. We can also apply this idea to cooking pasta. You know that when you cook pasta, you're supposed to add salt to the water. And basic gist is if you were at higher altitudes here, it would actually take longer to cook because the water itself is actually boiling at a lower temperature here. All right. If you're at higher altitudes, the pressure is less. So remember, boiling takes place when the atmospheric pressure is equal to the vapor pressure. So if the atmospheric pressure is lower, it's going to take less energy to make the vapor pressure and the atmospheric pressure equal. So essentially, your water is boiling at a lower temperature. So the pasta is not going to be cooking at the temperature you think. By adding the salt, by adding a solute, you lower the vapor pressure of the solvent, which means you need to add more energy here to make that vapor pressure be equal to the atmospheric pressure and boiling to happen. So basically what that means is the water would actually be boiling at a higher temperature, which is what you want to be able to cook your pasta. So you need to understand this idea that anytime you're adding a solute to a solvent, the vapor pressure of the solvent is going to be lower. We definitely need to understand this on a molecular level here. So being able to see this here, if you see this is a solvent on the left, you can see There are a few of the molecules that have entered the gas phase. That would be creating a vapor pressure if this was a sealed container. But now on the right side here, you can see that the solute was added. You formed a solution, and the solute is getting in the way, and you have less of those molecules of the solvent entering the gas phase, so it would have a lower vapor pressure. All right, again, same thing. If this is your pure solvent on the left side, you can see the amount of the molecules here that have entered the gas phase, creating that vapor pressure. But as soon as you add the solute and you're forming your solution, definitely have less molecules entering the gas phase, so it would have a lower vapor pressure. Anytime you're forming a solution, once you add that non-volatile solute, you're going to have the vapor pressure of the solvent being lowered. Again, on this slide, you can see this idea of the vapor pressure being lowered. If you just have the pure solvent here on the left, you can see some of those molecules are able to escape the liquid phase, enter the gas phase, creating a vapor pressure. But when the solute here is dissolved in the solvent, you can see it kind of blocks, and you definitely don't get as many of the molecules being able to escape the liquid phase, entering the gas phase, which creates a lower vapor pressure. This is just a funny slide where you can see the non-volatile solutes telling the solvent particles to calm down and stop trying to evaporate, because basically those solutes are going to lower your vapor pressure and prevent those solvent particles from entering the gas phase, which would create that lower vapor pressure. So again, anytime you're adding a solute to a solvent, the vapor pressure of the solvent is going to be lowered. This brings us to Raoult's law. The equation you can see here for Raoult's law is PA equals XA times P naught A. This is not on your equation sheet, so you would be given this equation. I would give you this equation on any quiz or exam, but you have to know what the actual terms mean and how to use it. So basically, the PA is the partial pressure exerted by the solvent above the solution. So this is going to be a pressure exerted by the solvent. XA is the mole fraction here of the solvent. That's very important. This is not the mole fraction of the solute. It has to be specifically for the solvent. So you will need the moles of the solvent over the moles of the entire thing here, of the total moles. And then this P naught A is the vapor pressure of the pure solvent. So essentially here, you have the vapor pressure of the pure solvent being multiplied by the mole fraction of the solvent to get your new partial pressure here, your new vapor pressure of the solvent. And we know that it should always go down. That's what we would expect to see here. Anytime you have the solute dissolved here in the solvent, we would expect that vapor pressure to be lower than the vapor pressure of the pure solvent. So now we can do a quick problem here using Raoult's law. This problem says we have glycerin, and it gave us the formula of glycerin is a non-volatile, non-electrolyte with a density of 1.26 grams per milliliter at 25 degrees Celsius. All right, so that's interesting. They're giving us a density here. We'll have to think about what that's going to be used for. It wants us to calculate the vapor pressure at 25 degrees Celsius of a solution made by adding 50 milliliters of that glycerin to 500 milliliters of water. They're giving us the vapor pressure of the pure water at 25 degrees Celsius, and we're given the density here of pure water. All right, so this is going to be a Raoult's law problem. We're trying to find the vapor pressure here of this solution. All right, and we know the vapor pressure of pure water, so we know that the vapor pressure of the solution should be lowered according to the colligative properties here, but we have to actually go about solving this. The equation we're going to have to use is that PA equals XA times P naught A. So we are solving here for this partial pressure, this vapor pressure of the solution. So in order to do this, we're going to need the mole fraction of the solvent, and we already are given the vapor pressure of the pure solvent. All right, so that's given. We're good with that. So it's going to be us needing to work on this mole fraction of the solvent. In order to do that, I need the moles of the solvent over the total moles here of the um, combined solute and solvent. So I need to figure out moles here. First thing to notice is that the glycerin is the solute in this case, and the water is the solvent. I'm going to need to figure out the moles of each though. So I already know here that I have 50 milliliters of the glycerin, and I have to figure out the number of moles of the glycerin. Well, this is where the density is going to come into play. Uh, the problem told me that there's 1.26 grams for every milliliter. So I know there's 1.26 grams here for every milliliter. That will get rid of the milliliters, and now I'm in grams, which I can get to moles here for the glycerin. So I know for every 1 mole of this C3H8O3, when you do the molar mass of that, there's going to be 92.094 grams. Your grams cancel, and now you're in moles of your glycerin. So when you plug and chug this with correct sig figs, you get 0.684 moles. And I'm just going to label that this is the glycerin so we know. All right, so now you have the moles of the solute. In order to do the mole fraction, you're going to need the moles of the solvent as well. We know that there's 500.0 milliliters of the water. All right, again, you're going to have to use the density here. The density is 1.00 grams for every milliliter. Milliliters cancel. Now you're in grams, so you can easily get this to moles. All right, so for every 1 mole of the water, when you do the molar mass of water, there's 18.016 grams. Grams cancel. Now you have the moles of your water here. All right, so when we plug and chug this with correct sig figs, I get 27.8 moles of the water. All right, so I'm on my way to finding the mole fraction here of the solvent, mole fraction of the water, but in order to do that, you're going to need the total moles. So you have to add these up, and when you do that, you get 28.5 moles here total. Okay, so I'm ready to do the mole fraction of the solvent, so I need the moles of the water over the total moles. So it's going to be the 27.8 divided by 28.5, and that's going to give me 0.975. Remember, there's no units here with the mole fraction. And again, we need to stress, you have to find the mole fraction of the solvent, not the solute here. Make sure you're dealing with the solvent, in this case, the water. So then in order to solve for the vapor pressure of the solution, you're just going to need to plug into the equation here. So PA is going to be equal to that 0.975 times the vapor pressure of the pure solvent. Well, the vapor pressure of the pure water was 23.8 torr. Obviously, you could convert this to any unit you want. It didn't ask for a specific unit, so you're just going to take the 0.975 times the 23.8 torr, which is your vapor pressure of the pure solvent, and when you solve that, it comes out to be 23.2 torr. Again, it didn't specify which unit we had to be in, so that would be the vapor pressure here of our solution. And if you look at this, it did decrease. The vapor pressure of the pure water is 23.8 torr, and the vapor pressure now of our solution, when we add our solute to it and form the solution, is 23.2, so it did go down. All right, so Raoult's law is a pretty simple equation. It's just sometimes you might have to do a little work to find that mole fraction of the solvent. All right, otherwise just plug in, make sure you know that equation, know what the letters mean, so you can use it here to figure out the value of a vapor pressure when you're forming a solution. The next property that is affected when a solute is added to a solvent is the boiling point. All right, when you're creating a solution here, the boiling point always goes up. All right, so as long as you have the presence of a solute, the boiling point will always be higher. Basically, the non-volatile solute causes the vapor pressure to drop, which we already talked about. So more energy must be added to get the vapor pressure of the solution to be equal to the atmospheric pressure in order to get it to boil. All right, so it ties in perfectly with the vapor pressure lowering. If the vapor pressure is lower, more energy is needed to make that vapor pressure equal the atmospheric pressure so boiling can take place. So it's always going to take more energy, or the boiling point is going to go up. And the easy way to think about this is that the solute gets in the way again of the solvent molecules and they cannot escape from the surface. So you have a higher boiling point here when you're creating a solution. Antifreeze is very helpful to allow your engine to operate at higher temperatures. Also, prevents it from kind of freezing up. And the idea here is, in terms of the boiling point, is that when you add the antifreeze, it basically increases the boiling point so the engine can work at these higher temperatures. And we already talked about how adding salt to water can increase the boiling point of the boiling water when you're cooking pasta. So the idea here is when you are creating a solution and you add the solute to the solvent, the boiling point is always going to be greater than the original solvent itself. We can see this here from this picture. Here is your normal solvent. You can see the molecules kind of leaving the liquid, turning into the gas. But when you add the solute kind of gets in the way, and less of those molecules are able to escape as a gas, which would lower the vapor pressure, which means in order to get it to boil, you're going to have to add more energy, and the boiling point is going to increase. This is just a funny little slide here. It says friends keep you cool. Essentially, these non-volatile solutes make it harder for the solvent particles to reach their boiling point. All right, it's going to take more energy. It's always going to have an increase in boiling point when you add a solute to a solvent to form a solution. There is an equation that goes along with this boiling point elevation. We have the change in temperature for the boiling point will be equal to Kb times the molality times I. So this equation is not on your equation sheet, so I would give you this equation, but you need to know what the different letters mean and how to actually use it here. So the change in temperature boiling point, this is telling you the change in the boiling point, the actual increase in the boiling point. Depending on what the question is asking for, if all it's asking for is what is the increase in the boiling point, that would be this. But if it wants to know like what is the actual boiling point now, you have to take this number and add it to the normal or original boiling point to get your new boiling point. Kb is this proportionality constant. It's dependent upon the solvent itself. All right, so it's a constant here that is depending on the solvent. M is the molality. So we've already looked at molality. We know the molality is the moles of solute for every kilogram of solvent. And I is this new letter here. It's the Vant Hoff factor. And we have to talk about what that actually is and how that works on the next slide. So this is the equation you will need to use for boiling point elevation problems, and you'll need to be able to actually do problems with this. Let's talk more about this Vant Hoff factor. All right, we already know that colligative properties depend on the number of solute particles here. So the amount of particles that form are important. We know that if you have an ionic compound that's soluble, they're going to dissolve, or more specifically, they're going to dissociate to give you 2 or more moles of particles for every substance that dissolves. So for example, if you are dissolving sodium chloride, or if sodium chloride is dissociating, you will form 1 Na plus and 1 Cl minus, okay? You don't just get one particle, you actually get 2 particles here, all right? So that's important. So if you were looking at the Vant Hoff factor or the I value for sodium chloride, it would be 2, all right? Because you get 2 particles forming when it dissolves or dissociates. Molecular compounds, on the other hand, covalent compounds, they don't dissociate in water. So if you took something like sugar and put it in water, for every one molecule you have of sugar, you're still going to have one molecule of sugar dissolving. All right, so there's no change in the number of particles. The Vant Hoff factor for any molecular compound, any covalent compound, is just going to be 1. All right, so just to look at a few other examples here, if you had something like CaCl2 dissolving in water, when that dissolves in water, you're going to get 1 Ca2 plus 2 Cl minus for every one of the compound. So 1 Ca2 plus, 2 Cl minus, that's a total of 3 particles. So the I value for that compound would be 3. If you look at something like ammonium phosphate here, when this dissolves in water, you're going to get 3 of the NH4 pluses, 1 of the PO4 minus for a total of 4 particles. So the I value for that compound would be 4. So you can see how this can change depending on the compounds. You have to look at the compound you're dealing with in your problem and then figure out what the I value would be. If the problem doesn't give you any information about I, you're just going to use I equals 1. Or if it's an organic compound, it's always going to be 1 because those are molecular compounds. But if you're given like an ionic formula, you have to be able to look at that formula and know, okay, this is what the I value is going to be. But if it's a larger molecule, an organic molecule, a covalent molecule, you just have to assume that it's 1. So you're going to use that Van Hoff factor here in these problems. Let's look at an example here. This problem says, at what temperature does a solution of 58.5 grams of salt dissolved in 1,000 grams of water boil? And they're giving you the Kb value, and they're also nice enough here to give you the I value. Even though it is salt, all right, sodium chloride, you would have Na plus and Cl minus, or 2 particles forming when it dissolves. So the I value is 2, but they were nice enough to give it to you in this problem and you don't have to figure it out. So we know the equation we're going to use here is the change in temperature of the boiling point is going to be equal to that Kb times the molality times I. All right. So we have to work on solving for things that we don't know here. We know that we're trying to figure out the temperature that this is going to boil. All right, so we're going to use the equation and solve for this. That's going to tell us the change in temperature, and then we'll have to add this value to our original boiling point. Again, this is water, so you should know the temperature water would traditionally boil at. We're going to have to add this value to the normal boiling point of water to get the temperature that this solution would be boiling at. So just be careful how the question is worded here. Kb was given. They did not give me the molality, so it looks like I'm going to have to find that, and we know I. So in order to find this change in temperature of the boiling point, I need to find the molality. Well, we know molality is moles of the solute per kilogram of solvent. They gave me the grams of the salt. That's the solute. Again, you have to identify the solute and solvent here. They gave me the grams of water. That's the solvent. All right, so I need the moles of the solute. So I'll take the 58.5 grams of the sodium chloride here. That's my solute. I'll get that to moles. All right, so for every 1 mole of that, when you do the molar mass, it comes out to be 58.44 grams. So your grams cancel. Now you're in moles. All right, and when you do this with correct sig figs, you actually have 1.00 moles of your NaCl, which again is your solute. But in order to do the molality here, we need the kilograms of the solvent. Well, the water is the solvent. They gave me the grams, so I'm just going to have to convert this to kilograms. It's a pretty simple conversion. We know there's 1,000 grams for every kilogram. All right, so we have just 1 kilogram here of the actual water. All right, and that's the solvent here. So in these problems, you do need to pay attention to the solute and the solvent. So if I find the molality, that's easy. It's just 1.00 moles over 1 kilogram. Remember, moles of solute for every kilogram of solvent. So the molality is just 1. So now we're ready to plug in. This change in temperature boiling point is what we're going to be solving for in the equation. They gave me the value of Kb, 0.512 degrees Celsius per molality. All right, I know it's weird units, but that's the only way we kind of get the molality units canceling so we can get degrees Celsius here for our change in temperature. We're going to times that by the molality, which is just 1 mole. And then we're going to times that by the Vant Hoff factor, the I value, which we know is 2. So when you plug and chug this and solve for the change in temperature here, we're going to get, with correct sig figs, 1.02. And remember, degrees Celsius are going to be your units that are left over. This is not your final answer. This is how much the boiling point will increase. All right, remember, when you're doing one of these problems with the boiling point always goes up when you dissolve a solute in the solvent. So this is how much the boiling point is going to increase, but we want to know what the temperature is that it will boil. Well, this is water. The normal boiling point of water in degrees Celsius is 100 degrees Celsius. If it was a substance that you didn't know the boiling point of, then they would have to give that to you in the problem. So the normal boiling point is 100 degrees Celsius. We are going up by 1.02 degrees Celsius. And when we plug and chug this, sig figs, it actually boils at about 101 degrees Celsius. So it does go up. Adding the salt to the water does make the boiling point go up a little bit. And that's what we expect here for one of these boiling point elevation problems. So you need to be able to use the equation, plug in, and solve. The next property we're going to look at here is freezing point. Anytime you add a solute to a solvent to form a solution, the freezing point is always going to be lower. All right, the freezing point of the new solution will always be lower than the solvent itself. So we call this freezing point depression. Basic gist, you have this solute causing the vapor pressure to decrease, like we already know. So less energy needs to be added here to get the vapor pressure of the solid and the liquid to be the same in order for it to freeze. A good way to think about it is that when you add the solute to the solvent, it kind of gets in the way of these solvent molecules, prevents them from kind of clustering together and freezing at the temperature that they normally would. So the solute's kind of getting in the way. This is how antifreeze works. All right, you add the antifreeze and it lowers the freezing point so that the engine doesn't freeze at the temperature you would expect. This is how salting the roads works. If you think about it, we add sodium chloride to the roads here in the winter. As it dissolves in the snow and ice and the water that's there, it actually lowers the freezing point of the water. So instead of the water freezing at exactly 32, it's going to freeze a little bit lower here. It only works to a certain temperature. Sometimes you can switch up the chemicals, maybe using calcium chloride, which might work a little better in colder temperatures, but you get the idea. Anytime you're adding a solute to a solvent, the freezing point of the solution is always going to be lower, all right, than the original solvent itself. This is how many plants and animals can actually survive the winter. They have a form of antifreeze, if you will, and it allows the temperature to drop without them necessarily freezing to death. So this frog or this plant here can actually survive the winter. And this is just a funny little slide that says friends keep you from freezing. Essentially, those solutes, when you add them to the solvent, they prevent the solvent from clustering together and freezing. So essentially, the solute lowers your freezing point and prevents that freezing from taking place. So anytime you add a solute to a solvent, the freezing point is always going to be lower. We can also do problems with this. The equation is very similar to the boiling point elevation equation here. So this time we have the change in temperature of the freezing point being equal to Kf, which is a proportionality constant that's dependent upon the solvent, the molality again, and I, the Vant Hoff factor, which you now know how to find and what to look for to find that. So just keep in mind again, this change in temperature freezing point is going to be the amount that the freezing point is going to lower by. If the question asks you what's the new freezing point, you have to actually subtract this value away from the normal freezing point to get the new freezing point, because the freezing point is always lower. So we're going to use this equation to do a problem now. This question says, what is the molar mass of nicotine if 1.921 grams dissolved in 48.92 grams of water causes it to freeze at negative 0.450 degrees Celsius, and they're giving us that Kf value here. All right, you should realize a lot of times these problems are used to find a molar mass. They can be very useful for finding a molar mass in the lab, so you need to know how to do these problems um, where you're finding the molar mass, not necessarily finding a freezing point, for example. So in order to do this problem, we know that we're going to need to use that equation. We have the change in temperature of the freezing point is going to be equal to the Kf times the molality times I. Now, anytime you are asked to find the molar mass here, you're going to end up needing to use the molality here. So you're going to have to solve this problem for the molality, and then we'll see how we can use the molality to get to molar mass. Remember, molar mass is going to be grams per mole. Right? And it's going to be specifically relating to the solute here. We're trying to find the molar mass of nicotine, which is our solute. So we already know the grams of the nicotine. They gave it to us right here, 1.921 grams. We need to find, well, the moles of nicotine. Right? Well, how do you find the moles of nicotine if you don't know the molar mass of nicotine? All right, so that's what we're going to end up solving this molality for and getting to moles, so we can do grams of nicotine over moles of nicotine to get the molar mass. All right, so we're going to need to plug in here the change in temperature freezing point. It tells us in the problem, water is now freezing at this new temperature. Well, the normal freezing point of water is 0. So our change in temperature of the freezing point is going to be 0.450. Be careful here. We're not going to put the negative in the problem because that wouldn't work. That would give us a negative molality. You know that the reason why it went lower is because the freezing point always drops when you're dissolving a solute in a solvent. So that is our change in temperature here of the freezing point. We're not solving for that this time. That's going to be equal to Kf, which we know is 1.86 degrees Celsius per molality, times the molality, which we said we're solving for. If you're going to be doing one of these molar mass problems, typically you're going to be solving for the molality, times the Vant Hoff factor. Well, they didn't give me any information here about I don't have a formula. This is not an ionic compound, so I have to assume this is an organic compound, so the Van Hoff factor just defaults to 1. All right, so that makes it easy. When you plug and chug this and solve for the molality, you get the molality equal to 0.242 mole here with correct sig figs. So that is the same thing as saying you have 0.242 moles of the nicotine all over the kilogram of solvent. All right, keep in mind it's the mole of the solute over kilogram of solvent for molality here. So we have to now always take the solvent, use the solvent here, and then use the molality to get to the moles of the solute. All right, so we know we have 48.92 grams of the water here. Well, that's the solvent, right? Sometimes it's helpful just to keep this all straight together here. So that's the amount of the solvent. We know, according to the molality, there's 0.242 moles for every kilograms of solvent. So if I can get to kilograms here, I can use the molality. So for every 1,000 grams, there's going to be a kilogram here of the solvent. Grams will cancel. Now you're in kilograms of solvent. And sometimes, like I said, keeping the solute and solvent straight here helps you know where you're at in the problem. So I'm going to take this molality, this 0.242 moles. Remember, it's the solute on top, all over the kilogram of solvent. So your kilogram of solvent cancels, And now you've successfully gotten to moles of your solute, which is what we're trying to do. We're trying to find the molar mass of nicotine. So we need the grams of nicotine for the moles of nicotine. And nicotine's the solute. All right, in order to do molar mass, that's grams per mole. So now we're in the moles of the solute, which is the nicotine. When you plug and chug and sig fig, it should be 0.0118 moles of your solute, or your nicotine. So now we're ready to do the molar mass of nicotine, grams per mole. They told us in the problem, all right? You got to go back, and this is where you got to be careful. You want to use the grams of the solute, not the grams of the solvent here. The grams of the solvent, along with the molality, gets you to the moles of the solute, all right? So I'm going back to the original problem, and the amount of the solute is 1.921 grams of the nicotine, all over the moles of the solute, or the moles of the nicotine that I just found, 0.0118 moles. When I plug, chug, sig fig, I get 163 grams per mole. All right, remember, that's your units here for molar mass. So you definitely need to be able to use this freezing point equation to be able to determine the molar mass of a substance. All right, so that's kind of a variation of this problem here, and it's actually very useful in lab. Another property we can look at here is osmotic pressure. Osmotic pressure is the pressure that would stop osmosis. Remember here, osmosis is the movement of the solvent through the selectively permeable membrane toward the higher solute concentration. Right, so this is more of a biology thing. So it's not like we need to understand the entire process a whole lot, but we can do some math here with osmotic pressure. Here is the equation we can use to find osmotic pressure. We use the pi symbol here to represent the osmotic pressure in ATMs. The capital M is the molarity of the solution here. R is the gas law constant, 0.082 liters times ATM over moles times Kelvin. T is going to be your temperature. That's going to have to be in Kelvin, obviously. And then I is the Vant Hoff factor again. This is a very good way to find the molar mass of an unknown. It can also be used, and it's better actually than freezing point depression or boiling point elevation here. So we're going to do a problem with osmotic pressure to find the molar mass of a unknown compound. This problem says to determine the molar mass of a certain protein, 1.00 times 10 to the minus third grams of it was dissolved in enough water to make 1 milliliter of solution. The osmotic pressure of the solution was found to be 1.12 torr at 25 degrees Celsius. We want to find the molar mass here of the protein. So we know the osmotic pressure equation here is going to be the osmotic pressure equal to molarity RT little I. Okay, so we're given the osmotic pressure, so we're not solving for that. In order to do the molar mass, the molarity is what we're going to use here to eventually get to the molar mass. So we're going to have to get grams per mole here, because that's molar mass. Well, if you notice, they gave us the grams of the protein. So we're going to have to use molarity to get to the moles of the protein, so I can do grams per mole. You just have to be very careful here with your units. Remember, R is this gas constant, and its units are going to drive our problem. So it's in liters times ATM over moles times Kelvin. So the first thing I notice is that the osmotic pressure is in torr. That doesn't work here. We need to get that to ATMs. So I have 1.12 torr, multiplication symbol, conversion line. We know that there's 760 torr for every 1 ATM. Torrs cancel. Now you're in ATMs, which is what we want. We plug chug sig fig, 0.00147 ATMs. All right, so that's going to be the osmotic pressure in ATMs, which is what we need. We cannot have the temperature in degrees Celsius. It needs to be in Kelvin. So degrees Celsius plus 273 equals Kelvin. So we got 25 degrees Celsius plus 273, and that's going to equal 298 Kelvin. All right, so it looks like now we're ready to plug into our osmotic pressure equation. We have the 0.00147 atms equal to the molarity, which is what we're solving for, times the 0.082 liters times atm over mole times Kelvin, times the temperature, which is 298 Kelvin, times the Vant Hoff factor, which this is just a protein. There's no information about its formula. We have to assume that it's kind of one of these molecular compounds. We're going to use 1 here for the value of I. All right, so now when you plug and chug this and solve for the molarity, you get the molarity being 6.02 times 10 to the minus 5th molar. All right, so remember, we have to do grams per mole here to get the molar mass. We have the grams of the protein. We need to get to the moles of the protein. Well, the only thing I know here is that I made 1 milliliter of solution. So I can use that along with the molarity to get to the moles. So I have 1.00 milliliters of the solution times, for every 1,000 milliliters of solution, there's a liter. And then this is where you get to use your molarity. Remember, molarity is moles over liters. So we know from what we just found, there's 6.02 times 10 to the minus 5th moles for every liter. Your liters cancel, and now you're in moles. When you plug and chug this, you get 6.00 times 10 to the minus 8th moles. That would be the moles of your solute. Remember, molarity is moles of solute per liter of solution. So the solute is the protein. You have the grams of the protein from the original problem. You now have the moles of the protein. You can do grams per mole to get the molar mass here. So we're going to have 1.00 times 10 to the minus 3rd grams all over the 6.00 times 10 to the minus 8th moles. That'll give us our grams per mole here. And when we plug, chug, sig fig this, it does come out to be 16,700 grams per mole. It's going to be 16,700 grams per mole here. You could also use 1.67 times 10 to the 4th grams per mole. That would be the exact same thing here. All right, so either of those answers work, but this is just showing you another way of how you can find the molar mass using osmotic pressure instead this time. You can actually see this boiling point elevation and freezing point depression on a phase diagram here. So if you look, the lines here are labeled. The solid black lines are the pure solvent, and then the blue lines are the solution where the solute is dissolved in the solvent. And if you notice here, you can see the freezing point of the original solvent and then the freezing point of the solution. Okay, so this line here would be the line that represents going between solid and liquid. So as you go from the liquid to the solid, that would be freezing. All right, so you can see here the actual area that would take place. But if you notice, when you form the solution, the freezing point would be here as you go from the liquid to the solid form. So this difference, this value here, this difference between those two lines would be your change in temperature of the freezing point. And then you can also see the same thing for the boiling point elevation. Here would be the area, all right, when you have your liquid to gas, all right, going to boiling, and then the solution would be here going from liquid to gas. This difference here between those two for the boiling point would be your change in temperature here of the boiling point. And it is increased. Notice the solution would have an increased boiling point but it would have a decreased freezing point, which is what we expect. So you can see this information on an actual phase diagram. Just want to make sure we point out colloids here before we're done. I don't hold you accountable for colloids, but it's more or less kind of just for your information. Colloids are solutions with particles that are too big to dissolve, but the particles themselves are too small to actually precipitate out. So they kind of become like suspended, all right? It's this line between solutions and heterogeneous mixtures, all right? So you have some tiny particles here being suspended. They're not going to dissolve, but they're also not going to settle out. That's a colloid. Something interesting that happens here is called the Tyndall effect. Uh, Light can actually get, you have this light particles being scattered here. So through a normal solution in which a solute is completely dissolved by the solvent, light just passes right through it. But a colloid would actually scatter the light because of those suspended particles. So you can see here, if you look at the pictures, this is showing you here the difference. A true solution, the light just passes right through, but the colloids solution here, you see actually this scattering of the light taking place. And that's what you would expect to take place in a colloid. Again, this is just a solution in which the particles really don't dissolve, but they're also not settling out. So they're kind of suspended here in the solution. Again, I don't hold you accountable for these colloids, but this is just showing you some of the different types here. You can see, there are foams, there are kind of emulsions and gels, and you can look at all the different examples. And again, this is not something you need to memorize. It's more or less just for your information. But these colloids are solutions, but they're not going to dissolve and they're not going to settle out. Just want to point out here, we are talking about solutions. You should be familiar with the solubility rules. So I wanted them in this video just so you could review them again if you need to. Remember, the first four here are referring to situations where the substances are soluble, with some exceptions here for insoluble. And then the last three rules here are focusing on when things are insoluble, with exceptions for soluble. So again, you need to know these solubility rules. They do appear sometimes in questions. Sometimes knowing these solubility rules makes it a lot easier to answer questions. So make sure you have all these solubility rules completely memorized.